Since its formation, our planet has undergone constant transformation. Stupendous collisions have created continents. Colossal forces have raised up ocean floors, forming dramatic mountain ranges. These movements on the Earth's surface can be seen today in the form of volcanic eruptions, earthquakes, and tsunamis. Tectonics sculpt our landscapes, modify the climate, displace oceans, and can even influence the living world. South America has the longest mountain range and the densest forest, the most powerful river, and the greatest biodiversity on the planet. It's a world of great beauty and infinite variety, forged by the energy contained within the Earth itself, shaped and molded by earthquakes and erosion. This turbulent past has left traces in rocks and cliffs. From the heart of the Amazon jungle to the lofty mountain peaks, scientists attempt to resolve the mysteries of the South American continent. One more tale in the never-ending story of the voyage of the continents. When it was born some 4.6 billion years ago, our planet was a gigantic ball of fire. Then it cooled, giving way to the first oceans and the first embryonic continents. As time passed, the emerging land masses came closer together, forming vast islands of terrestrial crust. 2 billion years ago, one of these continental masses, known as the Amazonian craton, became the cornerstone of the future South America. Nelson Rice works for the Brazilian Geology Service and is one of the leading experts on the history of the Amazonian craton. He's working in the north of Brazil, in the Tiepecem region. It is here that the last vestiges of this original land can be found, remaining unchanged since they were created. He explores the region relentlessly, looking for rocks that were part of the craton. It's a delicate mission, as the elements have changed the landscape over millions of years. Ancestral lands lie on the slopes of mountains with flattened tops that the Indians call tepui. For Nelson Rice, these rocky peaks provide valuable testimony for a better understanding of the origins of the South American continent. Over time, the Amazonian craton moved on the Earth's surface and collided with other land masses. 1.8 million years ago, it was trapped within the vise of a supercontinent, Columbia.
To reconstruct the story of the Columbia supercontinent, we need to do field studies. This involves collecting rocks for dating and studying what we call paleomagnetism. The data enables us to know the age of the rocks in question and also where they were situated in relation to the Earth's magnetic pole at the moment they were formed.
In recent years, Nelson Rice and his colleagues have collected and analyzed hundreds of samples. The results reveal a particularly complex puzzle.
Here in South America, we can observe at least 4 cycles of supercontinent formation. The oldest led to the formation of the supercontinent Columbia, followed by Rodinia, then Gondwana, and the youngest of them, in the Mesozoic, the Pangaea.
For millions of years, through tectonic plate movements, the future South America was therefore at the center of various differently shaped supercontinents. Today, the history of these successive assemblies is still little known. The surface of the planet has retained little evidence of these extremely ancient events. But at the University of Tucson in Arizona, one rather adventurous geologist has decided to investigate in order to reconstruct the various phases in the evolution of South America. He is Martin Bailey Pepper, a geologist and a motorbike fanatic. For several years, he has been exploring South America by bike, collecting unusual samples. Zircon, a mineral present in sand grains with the quality of being extremely stable.
What I really love about geology is that you can pick up just, let's say, a handful of sand here. And as a geologist, using the right tools, you can get in and just look at a single grain like a zircon. And you can take that single grain and you can zoom into that and get a whole story of not only when this formed, but you can go back farther, what fluids were there before this formed. You can also go forward and figure out so much information about the time it took to slowly come out of the deep mantle as these rivers were moved more and more off the top of these mountains, bringing this up from hundreds of kilometers deep, finally getting it to the surface. There's so much information into one of these grains of sand. And yet, that's almost the biggest thing we have when we go back billions of years to figure out what happened to things in Rodinia, or farther back to Columbia, or farther back to the beginning of the Earth itself.
Martin has already covered some 50,000 kilometers, from Patagonia to Ecuador. He's collected more than 8,000 samples from almost every river across the continent.
And so all I had to do was go into these river valleys with a gold pan, separate all the light minerals that I didn't want, and take just the zircon home. And it was those zircons that I could then take into our lab and analyze.
Back in his laboratory in Tucson, each grain of sand is washed, filtered, then analyzed using a laser. This process provides the precise age and composition of each grain of zircon. Martin hopes he will soon be able to identify the origin of all the sediment, and thus retrace the geological history of Latin America over 3 billion years. There are still years of work to be done, but already the first results are promising. The geologist has discovered grains of sand from every part of the continent that are some 900 million years old. This would suggest that at the time, all the fragments of land that make up South America were all assembled together.
When I think of the Earth, I like to envision it as almost like when you're cooking hot cocoa. And so you have the heat underneath the pot, and that causes this upwelling current, this convection cell. And the continents are really just these little marshmallow bits that float around on all that convecting magma. On Earth, as we know it, we see these giant continents. But when you go back in time, a continent is composed of these stabilized blocks. And it's these blocks that will actually separate and collide in time. And scientists have discovered that these blocks separate and coalesce into these supercontinents about every 400 to 500 million years. And these blocks can completely disassociate from what we understand as North America, South America, Europe, Asia, Africa. And so when we go to the time of Rodinia, the final assembly about 900 million years ago, many of these continental blocks that we would think of associated with South America look completely different. They were kind of in the middle of this supercontinent, but they were separated. And so after 900 million years ago, as all these blocks started to be ripped apart, we then disassociated what's something we wouldn't even recognize. And then they started to coalesce into something that we could finally say, ha-ha, that looks just like South America.
900 million years ago, the dislocation of a supercontinent would therefore have given rise to the future South America. The pieces of terrestrial crust that compose it began a long, common existence, and nothing would separate them. But subsequently, the continent would experience other dramatic changes. About 700 million years ago, the land masses of the southern hemisphere converged, and the future South America collided with the future Africa. This contact led to the appearance of a new supercontinent, Gondwana. The land today can tell the story of the birth of Gondwana, a major episode in South American history. We're in Rio de Janeiro, Brazil's second biggest city. There's a laboratory here with a very evocative name, the Gondwana Lab. It was founded by Renata Schmidt. Her objective is to understand every detail of every step in the formation of Gondwana. A century ago, it was the first supercontinent to be recognized as such by the specialists. It confirmed the hypothesis of the existence of plate tectonics.
It's like a perfect puzzle which fits together. So this was actually a very strong evidence for building up the theory of the continental wandering. This was in the 1920, more or less, and it evolved in 1950, 1960 to the theory of the tectonic plates. And it's just evolved much faster after the 60s because of all the knowledge we got from the oceans, because we didn't have access until the 50s, until the Cold War. And the Cold War, they started to build up submarines, and now they started to study all the oceans of Earth, and then we started to get better information, and then we understand that the continents actually are tectonic plates that move along the history of Earth since the beginning until today. The origin of Gondwana, the word Gondwana, comes from the 19th century when they found in India, in a region in India, Jaipur, and this region, there was this people, they call the Gonds. It's like an Aboriginal people. And they found there a sequence of sedimentary rocks of the Carboniferous period. And within these rocks, they found fossils of Glossopteris, which is a kind of plant. And the same sequence, the same flora sequence, they found in Antarctica, they found in the basins of Africa, and they found also in South America and in Australia. This is weird, like how can a plant travel from all this very large distance? So this mass, these continental masses should be together at some part of the history of Earth. And of course, another very strong evidence of the Gondwana amalgamation and the Gondwana existence is the fit of the continental margin.
For several years, Renata Schmidt and her colleagues have been studying the rocks of South America to learn more about the history of the supercontinent. Claudio Valeriano, a geologist at the University of Rio de Janeiro, is particularly interested in the famous Sugarloaf mountain, which stands majestically over the bay. This granite mountain, rising up 395 meters, is the result of a violent collision between tectonic plates.
This is a peculiar shaped rock that was eroded from a granite, a kind of granite that formed when some old continental blocks collided about 600 million years ago. The Sugarloaf is just an erosion form which was formed much later when Africa and South America broke apart.
When they collided, the rocks of the future African and South American continents folded and fractured. Magma rose to the surface, and gigantic mountain ranges emerged from the ground. Erosion then took over, and the granite peaks that dominate the Rio Bay today are all that remain of the monumental age-old relief. After 300 million years of coexistence, Africa and South America separated. It was a brutal dislocation, traces of which are still visible in the very heart of the rock.
We have here in Rio de Janeiro some rocks that testify this separation, which are the dolerite dikes. These are black rocks that fill fractures that were created about 130 million years ago. So these rocks, which we call dolerites, they filled these fractures, and they can be seen all around here and in the Sugarloaf area also.
Today, the Sugarloaf and the Corcovado are the best-known vestiges of that ancient collision. On the latter's summit stands the imposing statue of Christ the Redeemer, symbol of the city and indeed of the whole country. On the other side of the Atlantic, the coasts of Africa have also conserved traces of Gondwana's existence. In Namibia, the town of Keetmanshoop is in the heart of the Karas region. The landscape here was formed by the encounter between South America and Africa. As far as the eye can see, gigantic blocks of rock emerge from the plain. This breathtaking setting is where geologist Nicole Ulrich is hard at work.
This view now with the dune, I like this.
These rocks are strikingly similar to those found along the Brazilian coast.
Rocks that we see here in this beautiful valley give us evidence of plate tectonic processes. You do find similar rocks with a similar age on the other side of the Atlantic Ocean in Brazil. Like for instance, the world-known Sugarloaf in Rio de Janeiro is built up by similar rocks. This proves that the two continents, which are now separated by thousands of kilometers of ocean, have once been connected together, and only later, after the breakup of the Gondwana continent, were separated again.
When Gondwana broke apart, a vast ocean gradually opened up between the future Africa and South America, the Atlantic Ocean as we know it today. But this brutal dislocation made the Earth's crust fragile, and in places it was torn apart. Magma rose from the depths and seeped through cracks in the rock. Today, these lava inclusions are visible on Namibian soil and on the Brazilian coast. They form rather unusual seams called dolerite dikes. It is these rocks that Nicole Ulrich is researching and analyzing all along the Namibian coast.
Also in South Namibia, we can find evidence of the Gondwana separation. What you can see here are dolerite dikes. They occur in such great numbers that one cannot distinguish a single dike anymore, and this is why the geologists speak of a dolerite swarm. Dolerite is a magmatic rock that, compared to basalt, which flows out as a lava on the surface, does not reach the Earth's surface, but cools off in the Earth crust and forms long extending dikes.
Over thousands of years, erosion has brought the dikes to the surface. Today, they rise up towards the skies like rocky icebergs in the middle of the steppe. They remind us that Africa and South America were once brutally broken apart. After the separation, the South American continent began a long, solitary journey. It drifted slowly to the west, pushed by tectonic forces. But as it progressed, it encountered the gigantic Pacific Ocean plate. This new collision was not without consequences. Along the whole western face of South America, huge mountains rose from the earth. It was the birth of the Andes. Stretching over 7,000 kilometers from Venezuela to Chile, the Andes form the longest mountain range on the planet. They mark out the precise zone where the plates collided some 100 million years ago. It is in the central part, straddling Peru, Chile, and Bolivia, that the range is the most imposing. It is over 6,000 meters high and 1,700 kilometers long. It is also the focus of attention for Thierry Sempere, a geologist from the Earth Sciences Institute in Grenoble in France. He is heading for Tacna in the extreme south of Peru to retrace the region's geological history in as a detailed manner as possible. The land here has been stripped bare by centuries of erosion. For Thierry, the thousands of overlying strata are like the pages of a history book, an open-air geological archive.
So here we have some of the strata. As you can see, it's markedly stratified, with sediments deposited on a seabed. The sediments are very fine, very well stratified on the bed of a sea at least 1,000 meters deep. We're at an altitude of 2,000 meters, and so we can see that well before the Andes existed, we were in fact in an oceanic trench.
For a long time, the subduction of the Andes posed a problem for geologists. How did such marine sediments end up at an altitude of 2,000 meters? And above all, in what way could such high mountains be formed along a continent's border with an ocean?
It's true that most mountain ranges that have been studied in the past result from collisions like the Alps, the Himalayas, and others. Here, that's not at all the case. Throughout the region, the strata have not been deformed very much. They're like I'm doing with my hands, with a few undulations, but there are no folds, which would be like this. In the Alps, there are folds and thrust faults, an ancient rock that covers more recent rock, and in this part of the Andes, in the western part, we don't see that.
Most mountain ranges on the planet were created by the coming together of two continental plates. The Andes result from a very different phenomenon.
Everyone knows that the Earth is a ball, a sphere that's not exactly spherical, but almost. In its center is what we call the core, which is composed of iron, mostly in liquid form. Around the core is a kind of pulp called the mantle, and this mantle is covered over several tens of kilometers by a crust. In fact, the crust floats on the mantle, so the crust is subjected to Archimedes' principle. This means that the thicker it gets, the more it rises up, and that creates mountains. When the crust thickens, there's a substantial part we don't see beneath us, a bit like an iceberg, and there's a part that rises. and it rises at least 3 kilometers. These 3,000 meters that we've gained here are 3,000 meters that were produced by the thickening of the crust beneath our feet. And that thickening, with a rough calculation, would be around 20 kilometers.
In fact, the South American plate came into direct contact with the Pacific plate. As the latter was denser, it slid into the depths of the mantle. But the sediments that had accumulated on the ocean floor remained on the surface and were deposited along the junction of the two plates. This phenomenon led to the thickening of the continental crust, which then gradually rose. In the Andes, this terrestrial crust is now more than 70 kilometers thick in places, almost twice its normal depth. In the continent's extreme south, in the region of Torres del Paine in Patagonia, the Andes landscape is very different. Majestic peaks rise above deep valleys. The relief is chaotic, and the rock is a brownish color, its intensity contrasting with the hues of the northern Andes. The stories of the Andes formation here is more recent, and above all, much more complex. As it traveled to the west, the South American continent first of all encountered the Pacific plate. But a few tens of million years later, the southern tip found itself in a tight spot, where the Pacific and Antarctic plates were already face to face. The Earth's crust was therefore compressed, and vast quantities of magma rose to the surface. These infiltrations considerably raised the temperature of the surrounding rock, giving them this very particular color. The eternal voyage of the plates on the Earth's surface continues to change the face of Latin America even today. The continent continues to drift slowly westward, and its confrontation with the Pacific Ocean regularly causes the Earth to shake and move along the coast. This is notably the case in the region of Ilo in southern Peru. For several years, this small coastal town and the surrounding area have been carefully monitored by a team of scientists. Anne Soquet is a geologist with the Earth Sciences Institute in Grenoble and works in collaboration with the Peruvian Geology Institute. She is studying the movements of the Earth's crust thanks to a vast network of sensors installed along the coast. Today, she is on her way to inspect one of the GPS stations with a colleague, Nathalie Cotte.
Here we are. This is the GPS antenna. So on this site at Playa Meca, we've set up a relay next to this house, which is under surveillance, so there's no risk for the equipment.
The fact of having a station on the rocks is really good, to be sure that the type of readings we get are actually measuring the movements of the Earth's crust itself, and not just a superficial landslide or something that has nothing to do with what's happening with the subduction underground.
The antenna is linked to a GPS station, which picks up the ground movement data in real time. This is then safely guarded in a local fisherman's home.
Hello, sir.
Hi.
How are you?
Hello. Welcome to my home.
Thank you.
Where's the station now?
Here it is. Thank you, sir.
Thanks very much.
So let's take a look inside.
The apparatus is located just above the subduction zone, where the Pacific plate slides under the South American continent. The slightest movement, even minute, can therefore provide the geologists with valuable information.
The aim, in fact, is to look at the deformation generated by this subduction. The subduction involves a fault, which is blocked between two earthquakes, so it can generate huge quakes, megaquakes of a magnitude of 8 or even 9. Between two quakes, it's blocked in what we call the interseismic phase. During this phase, it's very important to measure the deformation. And I think here on this coast, we should have deformation of around 2 centimeters per year. So in fact, during the interseismic phase, the coast is moving towards the Andes Mountains. And during the coseismic phase, there's an elastic rebound, and we'll see a sudden displacement of around 5 meters, sometimes more. So we'll collect the data.
Between earthquakes, energy builds up in the depths of the Earth until it is released. But even today, predicting seismic events is an inexact science. Experts can't give a precise date for the next earthquake. But one day, they are certain the ground will shake again along the Peruvian coast. At the same time, more than 100 kilometers from the coast, Anne Soquet and her team are studying another phenomenon. The subduction of the Pacific Plate has created countless volcanoes here. Many of them are still active today and pour out torrents of lava at regular intervals. The town of Candarave in southern Peru lives constantly under the threat of the volcano Yucamane, which rises up some 5,500 meters.
This volcano is actually still active, and there's no doubt it presents quite a considerable risk for the town of Candarave, which is just below it.
Like all the volcanoes here in southern Peru.
There's a subduction zone with volcanoes behind it, except in a few places, so it's all part of the Pacific Ring of Fire. Why do we call it the Pacific Ring of Fire? It's because the Pacific is completely surrounded by subductions, and there are volcanoes all around the Pacific. But with these subductions, what they do, in fact, is make the oceanic plates disappear. So gradually, as they make the oceanic plates disappear, the Pacific will end up by closing. And as a result, North America and South America will come and join Japan and the Philippines, etc. And so the Pacific will disappear. It will be a new Pangaea.
This theory concerning the disappearance of the Pacific in a few million years is a controversial hypothesis within the scientific community. But for the moment, the Pacific Ocean continues to be slowly swallowed up in the depths of the Earth's mantle. All along the Andes, the encounter of the plates makes the ground quake and the volcanoes rumble. On the way back, Anne Soquet and her colleagues stop off a few kilometers from the coast. Once again, an analysis of the ground demonstrates that subduction is still going on. At this precise point, the ocean floor dives beneath the continental plate, and sediment has built up over the millennia.
In fact, about 40 kilometers beneath our feet, there's a subduction zone which generates earthquakes. But it doesn't just generate earthquakes, it also participates in raising up the Andes. We're very close to the coast here, and what we can see are different layers of different types of sediment. And when we take a closer look at these sediments, we'll see that there are shells, which were deposited by the sea. And here we're several tens, if not several hundreds of meters above sea level. So this shows that the subduction zone constantly generates deformation, and this constant deformation plays a part in raising up the coast. Perhaps we can go and take a closer look at these deposits? Have you seen it? It's really thick. It's more than 50 centimeters. Yeah, so you can see here, there are lots of shells, mostly bivalves. These deposits are quite recent in geological terms, between a few tens and a few 100,000 years. So the sea was here tens or hundreds of thousands of years ago. What's pretty here, in northern Chile and southern Peru, is that all along the coast, we can see the uplift, like this. There's a kind of coastal escarpment all along the coast in northern Chile, which continues here in southern Peru. This coastal escarpment can be several hundred meters high, and in some places, it's even a kilometer high. So that's quite considerable. And it shows that there was substantial uplift here, up to 1 kilometer in the past 3 million years. So this is associated with the subduction, and we really have considerable interaction between the Great Subduction Fault, which passes beneath our feet, and the coastal morphology and the beginning of the Andes deformation. Great, we've got a 10,000-year-old scallop.
A little further north, the geological history of the Andes is marked by another rather peculiar phenomenon. In the central sector, at an altitude of 4,000 meters, a vast plain has formed in the heart of the mountains. This is the Altiplano, the world's second highest plateau after the one in Tibet. We meet up again with geologist Thierry Semperi, who's continuing his research into the region's history. He comes regularly to the shores of Lake Titicaca on the border between Bolivia and Peru to study the origin and evolution of this unique ecosystem. Around a picnic, he explains some of the background to his young colleagues.
Do you know the twin or the species that's the closest cousin to the tomato?
No.
It's the potato. Because when the Andes rose up, the two species diverged. The tomato stayed lower down, and the potato adapted to the altitude. And it also invented a new strategy for reproducing, which is the tuber, which is actually a clone. Because it's cold on the Altiplano at night, and especially in winter, and in case the plant might die of cold, the tuber is always in the ground and can grow again. So that's one example of many throughout the world, and so when you form mountain ranges, you create whole new ecosystems.
Located 3,812 meters above sea level, Lake Titicaca is one of the highest navigable lakes in the world. It's in the heart of the Altiplano, trapped between two mountain ranges. Thierry Semperi and his team crisscross the region, taking extensive rock samples. For it's in the depths of the Earth's crust that can be found precious indications to the formation of this high plateau.
Oh, that's not bad. And there should be quite a lot of information inside if we can get the grains out, which will help to date it. On the Altiplano, the lowest regions are occupied by lakes because the Altiplano is a sort of closed basin. The rain that falls on the Altiplano doesn't go to either the Pacific or the Atlantic, but to the lakes that are scattered around the Altiplano. The biggest of them is Lake Titicaca, which is in the lowest region in this part of the Altiplano. What we have to understand, too, is that when we go down, beneath my feet, for example, after 10 kilometers down, maybe 10 or 12 kilometers down, the Earth's crust is fragile and cracks on the surface. But after that depth, it becomes soft and plastic. We say that it's ductile, and so, consequently, it behaves like plasticine, and it spreads out. It spreads out, and so as a result, the surface of the crust we're standing on naturally becomes flatter. The relief becomes less steep because we're on a kind of mattress, a mattress made up of 50 kilometers of plastic crust.
The Central Andes were in reality formed in several stages. When the Pacific Plate dips beneath the South American Plate, it raises up the continental crust, which is gradually deformed. An initial mountain range rises from the ground, the Eastern Andes. Then along the edge of the South American Plate, subduction heats up the terrestrial crust to the point of melting it. This fluid and malleable terrain enables the Altiplano to form and rise over millions of years. Later on, intense volcanic activity causes the uplift of a second mountain range, the Western Andes. The Altiplano is therefore now locked in on the western side.
We can clearly see behind me these very flat plains where people have settled. We have the water of Titicaca, and it's all surrounded by mountains which are not very high, quite flat, we might say. And right in the background, you can no doubt see the Eastern Andes. And you have to imagine that behind those snow-capped summits, we go very quickly down towards Amazonia, towards the Amazon forest.
The majestic landscapes of the Altiplano and the Andes Mountains demonstrate to what extent tectonic forces model and shape the land's destiny. But in turn, these mountains impose a considerable influence over the surrounding regions, and in particular, over the Amazonian forest. The small town of Gondwana in Peru is in the heart of the Amazon basin. It is here that a team of French paleontologists has set up their base camp. Every morning, the scientists respect the same ritual, a 30-minute boat ride before setting off into the jungle on foot. The team leader is Pierre-Olivier Antoine from the Evolutionary Science Institute in Montpellier in France. He's been exploring Western Amazonia for a number of years, studying the exceptional biodiversity here. With an area of over 6 million square kilometers, this tropical forest is the vastest and most diverse on the planet. Experts say it is home to 1.4 million species of plants and animals, half of all the species so far recorded around the world. On the ground, Pierre-Olivier analyzes sediment strata to see how the watercourse has evolved over time.
This is an extremely interesting site, which is unusual for the large variety of environments concerning the deposits we've noted. Here we have a first river coming in, which has very little energy. It would have been very calm, with just a few ripples. And then the energy level goes down further, and we basically find a marshland, a marsh with animals and plants that are typical of a marshland. And then quite suddenly, the energy changes, and there's a watercourse coming in with quite a strong current. So there we have a lot of detritus laid down, with larger elements forming a conglomerate. This lasts for about 2 meters, and above those 2 meters, we actually have a torrent, with large rocks washed along it, like this, so there was a very strong current. This current required relief, so obviously for that relief, we think of the Andes.
The scientists methodically examine the ground looking for fossils. Tiny clues hidden in the ground which could provide a detailed account of the history of the Amazon basin.
Here, in fact, we have an illustration of what we're after, meaning that we come to look for fossils, but these fossils have a particular interest, which is to gain a better understanding of the Amazonian ecosystem under the influence of the environment, and in particular, this environment which is linked to the Andes and the Andean tectonics.
Experts have known for a long time that the history of the Amazon forest is closely linked to that of the Andes Mountains.
It's a lower tooth.
Wow, it's spectacular.
During the growth of the mountain range, the basin was on several occasions filled with vast stretches of water, the last of which appeared about 12 million years ago. The scientists call it the Paybasse Sea. Until recently, the scientific community hotly debated a key question. Was it an inland saltwater sea or a freshwater lake?
So, do you know what that is?
Yes, of course. They're oysters.
Oysters.
But sea oysters, right?
Yes, of course. And last year, we took sediment samples here, and there were foraminifera, thousands of them, thousands of foraminifera.
I've never seen oysters here before.
So we're talking about an outcrop which is extremely unusual in the Amazonian context, because it's the only outcrop that has ostrea, or oysters, throughout Amazonia. Obviously, they are fossilized oysters, marine oysters, so they resemble the oysters we eat today. They have the particularity of having been perforated by organisms, which we call lithophagous organisms, which are marine creatures. This informs us directly that 12 million years ago, or in the past in any case, there was a sea here. In fact, these oysters represent the final obstacle for the opponents of the Paybasse Sea theory, who considered that this was a lake with fresh water, quite simply because no one had ever found oysters in the Paybasse system. But here we are. There are.
The whole of what is today the Amazon basin was therefore covered by a vast inland sea some 12 million years ago. The appearance of the Paybasse Sea in the middle of the South American continent is the result of plate tectonics. It is directly linked to the uplift of the Andes Mountains.
Through the effects of Andean tectonics, the Andes rose up about 15 million years ago. What we call the foreland, the zone that precedes the tectonized zone, the subduction zone, underwent flexure, or folding, and moved downwards. And in doing so, it allowed the sea to move in, an ingression of the sea. This Paybasse Sea then gradually withdrew, and the whole biodiversity of the Paybasse, with hundreds of species of mollusks and marine rays, and notably a whole bunch of crocodiles, which depended on that system, all these organisms would have disappeared at the same time as the system in which they lived. On the other hand, what's certain is that the disappearance of that very particular system enabled the current Amazonian system to be established.
Through its disappearance, the Paybasse Sea led to the extinction of thousands of animal species. But it gave way to the most powerful river in the world. An evolution that furthered the emergence of an incomparable biodiversity.
The luxuriance, the vast biodiversity of Amazonia, in fact, is ultimately very young. It's very recent in terms of what we know today. But it's not so surprising because that host of species was born out of tectonics, from the consequences of Andean tectonics, which over millions of years led to the separation of smaller basins, of the Amazon basin and lesser basins. And all those zones were separated slightly. They have slightly different vegetation and slightly different climates, and so all that led to distinctions among species, what we call the phenomenon of speciation. These sister species would then be either in the north or the south and would ultimately evolve independently and give us this whole biodiversity that we see today.
Amazonia bears irrefutable testimony to the bonds between the living world and geology. Unremittingly, plate tectonics shape and sculpt our planet. It gives rise to seas and oceans, to mountains and forests. 3 million years ago, another phenomenon radically changed the biological equilibrium of the South American continent. The closure of the Isthmus of Panama and the junction with North America. Isolated for some 50 million years, North America was therefore colonized by new species. Once again, the land changed shape and form, transformed by the perpetual voyage of the continents across the face of the planet Earth.